All right, I'm going to go ahead and get started. And so today we are going to talk about local maxima and minima of functions of several variables that we didn't get to last week. And then we're going to talk about absolute maximum and minima. Functions of several variables. That's like, a function of several variables on some domain. And then we're going to look at Lagrange multipliers. And then if we have enough time, get to double integrals. So let's start out with this problem pulled out of Stewart's calculus book, page 954, number 20 in the 7th edition. So show that this function has max values at plus or minus 1, comma 1 over root 2, and min values at plus minus 1, comma negative 1 over root 2. Also show that f has infinitely many other critical points, and d, the discriminant, equals 0 at each of them. Then determine which of them give rise to max values, minimums, and saddle points. So let's recall, how do we even find a critical point? A critical point can be found by taking del f of xy and setting it equal to 0. Right, the vector of partial derivatives equated to 0, then solve that system. So it would be a system of two equations because we have two variables in this case. So let's start off by calculating f sub x, which is the partial of f with respect to x. Okay, so now we need the product rule to evaluate this derivative. So we have, I remember it, the first times the derivative of the second plus the second times the derivative of the first. And let's clean this up. Let's factor out what we can. Let's see, we can factor out an e to the negative x squared minus y squared. 2, an x and a y. We're going to have 2xy e to the negative x squared minus y squared times, and then see, we have 1 minus x squared. So this is the first partial derivative of f with respect to x. And then we can do the same thing for f sub y, the partial of f with respect to y. And that turns out to be the first times the derivative of the second plus the second times the derivative of the first. Well, that's just going to be x squared e to the negative x squared minus y squared. Okay. Let's see, now we can factor. Once again, we can factor out an e, and factor out an x squared. So let's go ahead and do that. And we are left over with 1, that's minus 2y squared. Okay. So equating these to 0. Well, first let's note that this component of the function e to the negative x squared minus y squared is greater than 0 for all xy in R2. For any x and y that I plug into e to the negative x squared minus y squared, I will always get a positive number, a property of exponents, right? Now, if we let, suppose we let, x equals 0, and y can take on any real number, and y is any real number, then what do we get? We get that both derivatives equal 0, right, from here and here. So then 0 comma y is a critical point for all y and r. And that's where the infinitely many critical points comes from. Okay. So that takes care of, well, this component of the derivatives. The e is always greater than 0. We don't have to worry about that. Letting x be 0 will zero out f sub y and f sub x because of this x squared and this 2x term out front. Now we can strip it down to what's left is 1 minus x squared, 1 minus 2y squared. When those both equal 0, then we also get the gradient equals 0. Let's see, what do we get? Yeah, we have one equation equaling 0 and the other equation equaling 0. Okay, solving this for x, we add x squared over, we have x squared equals 1. Taking the square root, we have x equals plus and minus square root of 1 is just 1. On the other hand, we add 2y squared over, divide by 2. We have y squared equals 1/2. Y equals plus or minus 1 over square root of 2. This gives rise to 4 more critical points. Any possible combination of this x value, these two x values, and these two y values. So listing them all, we have 1 over root 2. We have -1 over root 2. We have 1 negative 1 over root 2, and then -1 negative 1 over root 2. And the instructions say, you go back up here, we have, it already tells us we have max values when the y component is positive and minimum values when the y component is negative. So let's go ahead and show that using the discriminant. Let's recall what the discriminant even is. So we say D is defined to be f sub xx, f sub yy minus f xy squared. And this really comes from the determinant of the Hessian matrix. So let's call that h sub f, at some point x comma y would be the matrix of second partial derivatives. If you've taken linear algebra, you can readily see, even from this class too, when you take a 2x2 determinant, what do you get? You do a d minus bc. So in determinant of this Hessian matrix, we get exactly the discriminant d. So that's what we're going to do. We're going to calculate all the second partial derivatives of our function. So go ahead and write, what fx was. Fx was 2xy e 1 minus x squared. Then fy was x squared e 1 minus 2y squared. Okay, so let's calculate f sub xx, right? That's taking the function f sub x and taking the partial derivative with respect to x. Okay, so now you can see we have like a triple product rule going on right here, because there's one function of x, there's two functions of x, and then there's another function of x. So let's recall how we do that in a single variable case. We want d dx of f of x times g of x times h of x. This is f prime of x, g of x, h of x, plus f of x, g prime of x, h of x, plus f of x, g of x, h prime of x. You fix two of them and take the derivative of the other and sum that all up. So that's what we're going to do. So f sub xx would be, okay, so if we take the derivative of the first, we get 2y, and we copy and paste the rest. And for the second one, we add 2xy. We get the derivative of the middle term, we get negative e, or e to the negative x squared minus y squared times negative 2x times 1 minus x squared. Then we add derivative of the last term, we get 2xy e negative x squared minus y squared negative 2x. Okay, that's horrendous, but we can factor some stuff out. So let's factor out obviously an e that appears in every term. And then let's kind of like distribute these polynomials out so we know what we actually have. So if we have 2y, 1 minus x squared, so this is 2y minus 2x squared y. And over here we have this 2xy, this negative 2x, and this 1 minus x squared. So that's going to be, okay, so that's going to be negative 4x squared y, 1 minus x squared, which is really negative 4x squared y plus 4x to the fourth y. And then over here, we have negative 4x squared y. Okay, so let's factor out, let's factor out an e, the negative x squared minus y squared. We can factor out, let's see, a 2y. I think that's it. We factor out a 2y. Right, this is really two terms right here because of this minus. And so I would be left over with 1 minus x squared. And then this one would be minus 4x squared. That'd be 2. I factor out 2 out of everything, x squared, and then we have plus 2x to the fourth, and we have minus 2x squared. If you see me make a mistake, let me know. But I think that's it actually. So the second partial derivative with respect to x is going to be 2y e to the negative x squared minus y squared. We combine like terms is negative 1, negative 2, so it's negative 3. Then negative 2 is negative 5. 1 minus 5x squared plus 2x to the fourth. Okay. This is the second partial of f with respect to x. And then let's do f sub xy, which is f sub yx, since we have continuity. And this is what? We get partial of f with respect to x and then respect to y. So we take, well, we don't need a triple product rule this time. That's good because 1 minus x squared is like a constant in y. So we have now the first times the derivative of the second with respect to y, plus the second times the derivative of the first. Okay, so this turns out to be, let's see, we can factor out an e, factor out, well, let's go ahead and distribute through. So we have 2, we have negative 4, so we have negative 4xy squared plus 4x cubed y squared times e. And then over here we have e negative x squared minus y squared times 2x minus 2x cubed. Okay. So if we factor out an e to the negative x squared minus y squared, and then we can also factor out single power of x. Yeah, I think that's it. So and a 2. Let's do 2x e negative x squared minus y squared. And then we get, let's see. Well, okay, so we have 1 minus x squared from this guy over here. And then we have minus 2y squared plus 2x squared y. Y squared. I didn't factor out a y. I factored out the e and the single power of x, that positive 2. Yeah, so this is it. Yeah, this looks good. Okay, so now we have f sub yy. So fy again was x squared e negative x squared minus y squared 1 minus 2 y squared. Okay, so f sub yy would be, let's see, we take the first times the derivative of the second. Let's just do the first times the derivative of the second plus the second times the derivative of the first. Okay, so this actually turns out to be, what do we have? We have negative 4x squared y e to the negative x squared minus y squared. Then we have minus 2x squared y e to the negative x squared minus y squared plus 4x squared y cubed e to the negative x squared y squared. Okay. Yeah, that looks good. And then we factor out an e. We can factor out a 2. We can factor out an x squared and a single power of y. So 2x squared y e to the negative x squared minus y squared times, and then we factor out, okay, let's do this one first. So we get 2 y squared, and then over here, these are like terms actually, so they add, that's negative 6, but we're factoring out a 2, so that's negative 3. And that looks good. Again, let me know if I make a mistake. All right. So we have all of our second partials. So we have to evaluate these second partials at our critical points and throw it into the discriminant formula. So f sub xx, let's do the point 1 over square root of 2 first. Well, f sub xx is this animal right here. So I get 2 times 1 over root 2. 2 times 1 over root 2 is really root 2. And I have e to the negative 1 minus 1/2. And I have, let's see, 1 minus 5x squared. X squared is just 1, plus 2x to the 4th is just 1 as well. Okay, so then I get, well, what does this turn out to be? This is negative 4, so negative 2. So this is negative 2 square roots of 2e to the negative 1 minus 1/2. This is less than 0. F sub xy, which is f sub yx, is equal to, okay, we have that dude right here. So we have, see, 2x is 2 times 1, just 2 e to the negative 3 over 2, 1 minus 1 minus 1 over root 2 squared is 2 over root 2 squared is 2 over 2, which is just 1. And we have plus 1, because we have 1 squared, 1 over root 2 squared. 1 over root 2 squared is 1/2. 1/2 times 2 times 1 is just 1. So this turns out to be 0. And then f sub yy is equal to, or, f sub yy at 1 over root 2 is equal to, we have f sub yy right here, 2x squared y, so this is going to be square root of 2 e to the negative 3 over 2. 2 divided by 2 is 1 minus 3. And again, we get negative 2 root 2 e to the negative 3 over 2. This is less than 0. Okay, so that means discriminant at 1 over root 2 is equal to f sub xx f sub yy is the same thing, minus 0. This is obviously greater than 0 because it's being squared and 0. Okay. So if we don't remember the rule about second derivative test for multivariable functions, we off to the side. If d is greater than 0 and fxx is greater than 0, we have a min. If d is greater than 0 and fxx is less than 0, we have a max. If d is less than 0, saddle point. So we have fxx being less than 0 and d being greater than 0. So we have a maximum at 1 over root 2. Which is what the problem said. So we could show, again, f x x negative 1 over root 2, f x y fyx negative 1 over root 2, and fyy negative 1, 1 over root 2. Okay. And I encourage you to verify this yourself by plugging in the values. But since x is being squared, 4 raised to the 4th power, and y is the same, based on our functions, we have the same output for these two critical points. So this is less than 0, this is equal to 0, this is less than 0. So that means d at negative 1 over root 2 is greater than 0, and fxx is less than 0. Therefore, we have a max at 1 over root 2, negative 1 over root 2. Okay. So now we have to show the mins. I'm going to show one of them and do a similar. So now for the mins, plus minus 1, negative 1 over root 2. We have fxx, positive 1, negative 1 over root 2. We get negative root 2 e to the negative 3 over 2. Times 1 minus 5 plus 2. Again, this is going to be 2 square roots of 2 e to the negative 3 over 2. This time it's positive. And then fxy equals fyx equals 0. Fyy 1 negative 1 over square root of 2 is equal to, let's see, where's fyy? There. Okay, so we have 2x squared. This is 2 times 1 divided by negative root 2. So this is negative root 2 e to the negative 3 over 2. And then we have 2y squared minus 3. Y squared keeps it positive, returns it positive. And then we have 1 minus 3. This is positive 2 square root of 2 e to the negative 3 over 2. Okay? So if we do fxx fyy minus fxy squared, this is 2 square root of 2 e to the negative 3 over 2 squared minus 0 is greater than 0. And then, so this is, d is greater than 0, and fxx is greater than 0. Therefore, we have min value at 1 negative 1 over root 2. And similarly, we have the same output for negative 1 over root 2. Yeah, this being greater than 0, then fxx being greater than 0 as well. So we also have min at negative 1 over square root of 2. You can verify that. Okay, so that classifies those 4 critical points, but we still have infinitely many critical points to classify. We're going to do that by sectioning them off by positive, negative, and 0. So these other critical points we said occur where x is 0 and y is any real number. So we're going to show that d equals 0 for all such points. So that is d of 0 comma y is equal to, we have fxx 0 comma y, fyy 0 comma y minus fxy 0 comma y squared. Fxx 0 comma y, well, here's fxx right here. Am I missing an x or something? Let's see. This is fxx right here. If I plug in 0, I don't get 0. Maybe there should be an x in this term right here. In fact, something factored out. I'm missing. Okay. Okay, it's the bottom of this. So if I do the Symbolab, the function is x squared y e to the negative x squared minus y squared. Go. Okay, let's just proceed. So I plug in 0 for x and y for y in fxx. I get 2 y e to the negative x squared minus y squared. Fyy at 0 comma y is, you see, we get 0 here. It's probably some silly mistake I'm making. fxy, let's see. And we get 0 there too. Oh, I'm dumb. Yeah, okay. This is non-zero, but these two are 0. Okay. And so when we plug it into this formula, we get d of 0 comma y is equal to 2y e to the negative y squared times 0, which is times fyy, minus 0 squared. This is obviously 0. Okay. So we showed that for the critical points, 0 comma y, d is equal to 0. Therefore, second derivative test is inconclusive. So what do we do? Let's look at the little region in question that's all the critical points. So if x is 0 and y is any real number, That means our critical points lie along the y-axis. Okay? So let's examine what the value of f is along this line, along this red line right here. That is, what is f of 0 comma y? Well, remember, f of x was x squared, y, e to the negative x squared minus y squared. So this equals 0 for all y in R, right? Because of this guy right here, x squared. 0 squared times any real number is always 0. So that's the function value at these critical points is 0. And so let's look at, like, say we have a point above the x-axis. We're looking at what are the values around here. Because remember, so a local max is f of x naught y naught greater than or equal to f of xy for all xy near x naught y naught. So we're going to do that. So if I take a step over here in this direction, that's like a little tiny step in the x direction. Or if I take a little step over here in the negative x direction, I'm going to observe what happens to our function value. So I'm going to say let epsilon greater than 0 be given. It's arbitrarily small. It can be, just represents a small number. But and it's a small positive number. So when I plug in f of epsilon y, what do I get? I get epsilon squared y e to the negative x squared minus y squared. Also let y greater than 0. So we're just dealing with everything above the x-axis. So y is positive, e squared is positive, and this e is, or epsilon squared is positive, and this e is always positive, so this is greater than 0. And let's look if we take a step in the other direction, we get negative epsilon squared y e negative epsilon squared minus y squared. This is the same thing as f of epsilon y, which is greater than 0. Therefore, for all xy near the point 0 comma y is greater than 0, we have that f of 0y is less than, because it equals 0 at this point. Everything else is positive. Minus the times where we just step forward, then it would just be equal to. Well, I put less than or equal to sign so that works. Therefore, this fits the definition for a local minima. Min along 0 comma y, where y is a positive real number. On the other hand, if we look below the x-axis, so I'm going to say, let y be less than 0, and we're going to observe a point down here. What happens if I take a step to the right, a step to the left? Well, f of 0 comma y is still equal to 0. But f of epsilon y, what would have to happen to epsilon y? Well, we get epsilon squared y e to the negative epsilon squared minus y squared. Y is negative, epsilon squared is positive, e is always positive, so this is less than 0. And then the negative epsilon changes nothing because all x's are being squared. This is also less than 0 because it equals f of epsilon comma y. So then we showed that f of 0 comma y equals 0 and f of epsilon comma y equals f of negative epsilon comma y is less than 0. Therefore, for all xy near 0 comma y, where y is less than 0, f of 0 comma y is greater than f of xy. This fits the definition of local max. And then for the argument for the origin, when y is 0 and x is 0, it has to switch between being a local max and a local min. So f of 0, 0 has to be a saddle point. So we just classified infinitely many critical points, plus 4 of them. So that finishes that problem. On to the next one. Global max and min of f on D. Okay, so we have a function of 2 variables. This would be, if I'm not mistaken, well, yeah, the x squared y kind of might throw it off a little bit, but it's like a paraboloid almost. So let's look at D in the xy plane. Positive value of x is less than or equal to 1. X lies in between -1 and +1. Same thing with y. This is D. Everything on the border of this and in the interior. So what we're going to do is find critical points in interior of D, and then we're going to parameterize. This is the boundary of D. And plug into f of xy, which we will then maximize or minimize. Okay, so critical points in the interior of D, we have the gradient of f of xy is equal to, we have 2x plus 2xy, 2y plus x squared. Well, if we have 2x times 1 plus y equals 0, and then 2y plus x squared equals 0. What do we get? So this f right here has 2 solutions. Let's start with x equals 0. If x equals 0, first equation equals 0, then the second equation would be 2y plus 0 squared equals 0, which only works when y equals 0. That means 0, 0 is a critical point. On the other hand, if from this equation, this first equation, if y equals -1, we have in the second equation 2 times -1 plus x squared equals 0. X squared equals positive 2. X is equal to plus or minus square root of 2. So we have points plus minus root 2, comma -1. But this is a bummer because the absolute value of square root of 2 is greater than the absolute value of 1. So these critical points are not included in our domain. We can throw them out. So the only critical point on the interior of D is the origin critical point. Okay. So let's go ahead and evaluate what f of 0, 0 would be. F of 0, 0, what do we get? So it's polynomial with a plus constant would just be 4. It's 4. All right. Now let's look at the boundary. So we're going to parameterize the boundary and plug that into our function. we have like the unit square. We have C1, C2, C3, C4. Well, C1 is really, well, it's x is 1 the whole time, y is y, such that y ranges in between -1 and +1. C2 is, what do we get? We get 1 for y, x, such that -1 is less than or equal to x is less than or equal to 1. C3 is -1 for x, y ranges from -1 to +1. And C4 is x -1, such that x ranges in between -1 and +1. Okay. Then we have, our function f of xy equals x squared plus y squared plus x squared y plus 4. Plugging all these values in, we have f of 1 comma y is equal to 1 plus y squared plus y plus 4, or y squared plus y plus 5. That was for C1. And if we try to set the derivative of this equal to 0, we get equals 0, -1/2. And think about this. Okay, so then we would get 1 -1/2. And let's look at f of 1 comma -1/2. What do we have? We have 1 plus 1/4 minus 1/2 plus 4. This is, well, that's 5. And this is -1/4 minus 1/4. Let's just leave it like that. Okay. And so since this is on like a closed domain and we're looking for the absolute, you just find all the critical points and then compare them. Just whichever one's the smallest is the minimum, and whichever one's the biggest is the absolute max. Okay, so then we have f of C2. C2 is x comma 1, which would be x squared plus 1 plus x squared plus 4. We have 2x squared plus 5. We set this derivative equal to 0. We have 4x equals 0. X equals 0. Y equals 1. So x is 0. Y is 1. Get that guy. And x is 0, y is 1. We have y squared plus 4. Well, y is 1, so it's 1 squared plus 4. So this is 5. Okay. Now if we look at f of C3, -1 y, f of xy is x squared plus y squared plus x squared y plus 4. We have 1 plus y squared y plus 4. Well, it's the same thing as earlier, right? We have y squared plus y plus 5. So that puts us y equals negative 1/2. And the derivative equals 0, so then we have negative 1/2, negative 1. Okay. So f of negative 1/2, negative 1 is going to be 1/4 plus 1 plus negative 1/4 plus 4. This is 5. So definitely not a min or a max. We can throw this out because so far our minimum is 4, and that occurred at the origin. And actually 5 is the max for right now. Okay. And then we have f of C4 f of C4 is f of x negative 1, which is x squared plus 1 minus x squared plus 4. This is equal to 5. This is not equal 0. Okay. But since this function is like monotonically increasing as y gets big and x get big, then we have to check like the extreme values of the of our shape. That is, like, we have to check these corners right here. Oops, where's my okay, here. So this was 4. What is this point? This is 1, 1. And this point, negative 1, positive 1. Right, because x is being squared, so the negative doesn't affect it. It's sort of like symmetric about the y-axis and that. And then having the greatest value for y would probably maximize it. So let's look at this. We have f of 1, 1 is 1 plus 1 plus 1 plus 4, which is 7, which is the greatest so far. And then same thing with f of negative 1, positive 1, we also get 7. So we have absolute max of 7 at plus minus 1, 1. And absolute min of 4 at the origin. Okay, method of Lagrange multipliers. Let's see. So let's say we have a function of 3 variables. Subject to one constraint. That is the level set g xyz equals some constant. You have to find all x, y, z, and lambda such that the gradient of f of x, y, z is equal to lambda gradient of g x, y, z. And the equation g of x, y, z equals k. So then you evaluate f at the above points. Largest is max. Smallest is min. And then just, for completeness, we have if we have two constraints, we do the following. We solve this system instead. The gradient of f is equal to lambda gradient g1, one of the constraints, plus a different multiplier gradient of the other constraint. So that's what we're going to do in this next problem. Use the method of Lagrange multipliers to find absolute max and min of values of function of two variables on the ellipse. And this ellipse is actually a disk because it's less than or equal to. So we have to check the interior and the boundary. We're going to use, to check the boundary, Lagrange multipliers. To check the interior, just set the first derivative equal to 0, the partials. So let's see. So let's do that first. We have the gradient of f of xy is equal to 4x minus 4, 6y minus 4. This is when this equals 0, when x equals 1, y equals 2/3. And clearly this is in the interior of D, or E. Okay, so that's one thing we have to consider. We also have to do the method of Lagrange multipliers for the boundary. So for the boundary, our function g is 2x squared plus 3y squared equals 30. We do gradient f equals lambda gradient g. Well, gradient f we said was 4x minus 4. This equals lambda times 2x. We have 6y minus 4 is equal to lambda 6y. Okay. So let's see what we can do. Take this guy, I subtract the lambda 2x over, add 4. So we have 4x minus 2 lambda x is equal to 4. And we have 2x, we have 2 minus lambda equals 4. There should actually be a 4 right here. So then that would turn into factoring out a 4, and then we have a 1. Okay, yeah. And then the rest is okay. Okay, so now we solve for x in terms of lambda. We have x is equal to 1 over 1 minus lambda. On the other hand, if we do the same thing with y, we get 6y minus lambda y is equal to 4. 6y, 1 minus lambda is equal to 4. We have y is equal to 2 over 3, 1 minus lambda. Now we plug this in for g, and we have g as a function of x and y. Plug in x in terms of lambda, y in terms of lambda, and then solve for lambda. Then we can have, we have explicit solution of x in terms of lambda and y in terms of lambda. So then we just, we immediately have x and y. So we're going to plug in x and y into 2x squared plus 3y squared equals 30. So this is going to be 2 over 1 minus lambda squared plus 3 times 4 over 9, 1 minus lambda squared is equal to 30. These cancel. If I hit everything with the 3, that would be 6 plus 4, 1 minus lambda squared is equal to 30. So that's 10 on the numerator, divide by 10. Oh wait, no, divide by 30. Just cross multiply that or whatever, and then we have 1 over 3 equals 1 minus lambda squared. 1 minus lambda is equal to plus or minus 1 over root 3. Let's add and then subtract. We have lambda is equal to 1 plus or minus 1 over root of 3. So we have two values for lambda, then we have two values for x and y. So if lambda equals 1 plus 1 over square root of 3, then what do we get for x? Oops. For x, we have 1 over 1 minus lambda, and y was 2 over 3. So then x would be 1 over 1 minus 1 minus 1 over square root of 3. Cancel, cancel. Divide by a fraction, you flip it, so it's negative square root of 3. And then on the other hand, y would be the same thing, just multiplied by 2 over 3. This is 2 over 3 times square root of 3. Or you could write it as that, same thing. So then that's, one critical point on the boundary, negative 3, negative 2 over root 3. But on the other hand, if lambda equals 1 minus 1 over square root of 3, what do we get? We have x is equal to 1 over 1 minus 1 plus 1 over root 3. It's just positive, and then that means y would be positive. Now we have three critical points. We have negative root 3, negative 2 over root 3, root 3, 2 over root 3, and then we also have from the interior 1 comma 2 root 3. Okay, what do you do? What do you do next? Oh, okay, you just plug in the values. Find f of negative root 3, negative 2 over root 3 equals something. F of root 3, 2 over square root of 3 equals something. And then we have f1, 2 over 3 equals something. Oh, why did I do 0? Yeah, okay, and then some numbers, and you would compare, take the biggest one to be the max, the smallest one to be the min. It turns out that the max is this negative root 3. It is a maximum of 9 plus 20 square root of 3 over 3. And this one right here is the min at 9 minus 20 square root of 3 over 3. This is the max. This is the min. Just computational stuff. All right. Chugging along, we have extreme values subject to 2 constraints this time. Okay, so let's go ahead and hop into it. We have the gradient of f is equal to lambda gradient g1 plus mu gradient g2. Then we get 1, 2, 0 is equal to lambda 1, 1 plus mu 0, 2y, 2z. If this is G2 and this is G1. So then, we have the system. We have 1 is equal to lambda, the very first one. The second one, we have 2 is equal to lambda plus 2 mu y. From the third one, we get 0 is the same thing as y plus 2 mu times z. Well, this is a really nice problem because they give you lambda equals 1 from the very first equation. That's nice. So then that means that 1 is equal to 2 mu y, and that means negative 1 is equal to 2 mu z. So we have y is equal to 1 over 2 mu, and z is equal to negative 1 over 2 mu. We have a function y of z, or a function of y and z, as one of our constraints. So we're just going to plug in y and z and find mu. So we have 1 over 4 mu squared plus 1 over 4 mu squared is equal to 4. Hit everything with the 4, and we have 2 over mu squared is equal to 16. So mu squared is equal to 1/8. So mu is equal to plus or minus 1 over 2 square root of 2. So if mu is equal to the positive, then what do we get for y? For y, we get 1 over 2 square root of 2. So we just get root 2. And then z would just be the negative of that. So if y is equal to square root of 2 is equal to negative z, then x plus root 2 minus root 2 is equal to 1. X equals 1. This is our other constraint equation, the plane equaling 1, the affine function. Okay. Now we have a point 1, root 2, negative root 2. We will compare that to if mu equals negative 1 over 2 root 2. And then what do we get? We get, well, we just flip the sign of everything. We have y is equal to negative root 2, z is equal to positive root 2, x is still 1. So we have 1, negative root 2, square root of 2. We have 2 critical points. And then you can show that f of this bad boy is 1 plus 2 root 2. And f of this animal is 1 minus 2 root 2. This is the min and this is the max. Awesome. Okay, let's do this one real quick. And then I'll leave the other one for next time. Sketch the solid whose volume is given by the iterated integral. Evaluate. Okay, so right, if we take a double integral, I forgot about this. I'll probably just talk about this and then resume next time on that integral. But okay, so if the definite integral from a to b of f of x dx finds area, and f of x is greater than or equal to 0, what does the double integral of a function of 2 variables find on some region? I wish people were here so they could answer my questions, but I'm all by myself and I'll have to answer it myself. This finds volume. Okay, when f of xy equals 1, what does the integral find? And since I'm alone in this, this integral finds area. Therefore, this definite integral from a to b of 1 dx would find length of the interval. You can easily verify that by integrating and then doing, big F of b minus big F of a in the fundamental theorem of calculus. And then triple integrals, well, if you have the triple integral of some region, you're integrating a function this gives you, I don't know, there's not really a way to interpret it geometrically. Sort of like a hypervolume, or you could think of it like a density. If f is a density function of some object, or a mass function, something like that, yeah. But on the other hand, if you had e integral over e of 1 dv, this would find volume. So when you have the special integrand as 1, it bumps it down a dimension. And with that, I'm going to close. I'm going to go ahead and show you this problem. You can take a crack at it if you want, or you could try this one as well, but I'm going to do it next time. So thanks for watching.